The ability of an AI to learn depends heavily on what we might call its speedometer. This speedometer allows the AI to measure and adjust its own performance. While calculus often seems intimidating, it is fundamentally just the study of change. In the context of AI, we use derivatives to measure the effect of tiny adjustments. Imagine the AI has a control board. When it turns a specific knob or slider within its brain, it needs to know how that tweak affects the outcome, which we see here as the final error. By understanding this relationship, the AI learns whether it should turn those knobs left or right to improve its accuracy. To understand how this works without any complex math, let's look at this hilly golf course analogy. Imagine you are an AI standing on a hill right here at this current spot. It's night, and you are surrounded by thick fog. Your ultimate goal is to reach the very bottom of the valley because that lowest point represents the lowest possible error for the AI. Because of the fog, you cannot see the bottom, but you can feel the slope of the ground beneath your feet. If you feel the ground sloping downward, you take a step forward. If, on the other hand, the ground begins to slope upward, you realize you have gone too far and must step back. The measurement of that slope where you are standing, that is exactly what a derivative is. It tells the AI both the direction and the steepness of the hill it is currently on. Let's bring this down to a familiar scenario, because a derivative is simply a rate of change. Consider a truck delivering goods. Its position tells us where it is right now. If we want to know how fast that position is changing over time, we take the derivative of its position. That gives us its speed, as seen on this gauge. If we then want to know how fast the speed itself is changing, we take the derivative of the speed. This calculates acceleration, represented by this rocket. So the most important thing to remember is that taking a derivative simply tells us the rate at which something is changing over time or space. Next, we will look at the mathematical equation that actually calculates this precise rate of change.
So, we know we need to measure change to help our system learn. In mathematics, we call this measurement the derivative. You'll often see it written symbolically as f prime of x or sometimes as a fraction like dy over dx. But don't let the symbols intimidate you. No matter how it is written, it is always asking one fundamental plain English question. If I increase my input x by just a tiny amount, how much does my output y change? Let's break down exactly what that means using this graph and its corresponding limit equation. Imagine we are at a specific point on a curve. We start with our current input x. Plugging that into a function gives us a current value f of x, which corresponds exactly to this blue spot right here on the curve. Now, we want to measure change. So we give our input a tiny little push to the right. We call this tiny nudge h. By adding h to x, we arrive at a new input position on the axis x plus h. Because we moved our input, our output has to respond and change too. This brings us up to a new value after the nudge, which we write mathematically in the equation as f of x plus h. You can clearly see that new higher red point over here on the graph. To find the actual derivative, we simply compare these changes. In the top part of our big equation, we take the new value minus the old value. This subtraction gives us the total change in our output. Then we divide that by the change in our input, which is just our tiny nudge h right here in the denominator. By dividing the change in output by the change in input, we are calculating a slope. But we want the exact slope at that very first blue point. So, we make our nudge h incredibly small, shrinking it down so it approaches 0. That's what this limit as h approaches 0 notation means. As that gap shrinks, our estimated slope becomes the true tangent line slope. The key takeaway here is that a derivative is simply a precise mathematical tool to measure the slope, telling us exactly how sensitive our output is to tiny changes in our input. Speaking of slopes, let's picture a robot on a steep playground slide to see how this relates to finding errors.
We just talked about derivatives as a way to measure how a tiny nudge changes our output. Now let's see how an AI uses this exact math to learn using something we are all familiar with, a playground slide. Imagine our AI is this little robot starting at the very top of the slide.
Up here at the start, the error is very high, meaning our AI model is currently making a lot of mistakes and hasn't learned much yet. But notice the ground right where the robot is standing. It is completely flat, which means the slope is zero. Because there is no steepness, the mathematical derivative is also approximately zero. Now as the robot pushes off and goes down, he enters the middle section of the slide. Here, the physical slope becomes very steep. In calculus terms, the derivative here is a high number, which tells the system there is a rapid change happening. Because the AI is sliding downward along this steep gradient, its overall error is rapidly decreasing. It's learning quickly. Finally, the robot reaches the bottom. Look at the robot safely landing in the sand. The ground here flattens out again, meaning our slope naturally returns to zero. We call this flat area the error valley. This is exactly where we want our AI to end up, because it represents the state of lowest possible error. Just like at the top, since the surface is flat, the derivative is once again essentially zero. The ultimate goal of an AI training process is to use the derivative to follow the steepest slopes downward, searching for that flat spot where the slope equals zero, because reaching that bottom valley means it has achieved the lowest possible error. Understanding how fast things are changing isn't just for AI finding the bottom of a curve. Engineers use these exact same principles to monitor dangerous pressure spikes in industrial facilities.
Now that we've seen how the slope represents our error, let's look at how derivatives are actually used in practice. In industrial settings like an oil refinery, derivatives are absolutely vital for safety. Sensors are placed on pipes to constantly monitor the internal pressure. If the pressure is currently at 100 psi, the system might seem safe. However, engineers look at the derivative of that pressure. If the derivative is positive and increasing rapidly, it tells us the pressure is spiking at a dangerous rate. By monitoring this rate of change, the system can instantly trigger a safety valve to prevent an explosion rather than just waiting for the current pressure to hit a critical limit. We also see this in our daily lives. Digital services like Netflix use derivatives to provide a smooth, buffer-free viewing experience. The system uses AI to constantly adjust and find the best video quality or bitrate. By calculating the slope or derivative of buffering changes, the AI finds the perfect balance, the highest possible picture quality where the buffering rate stays precisely at zero. So, how do we actually program this? Developers often use a Python library called SymPy to handle this symbolic math. Let's walk through a typical script. First, we define x as a mathematical symbol rather than just a standard variable. Next, we define our AI's error function, which in this case is x squared plus 5x plus 10. Then we find the derivative. Using the diff command, the computer applies the power rule. The x squared becomes 2x and the 5x becomes 5. Our resulting formula is 2x plus 5. Finally, we calculate the steepness at a specific point like x equals to 2. We just substitute 2 into our new formula, giving us a slope of 9. This tells the AI that at this exact spot, the hill has a steepness of 9. To bring it all together, remember these core rules. First, if the derivative is positive, the hill is going up. Second, the derivative of a flat horizontal line is 0. And third, the AI always wants to find where the derivative is 0 because that's the bottom of the valley, the point of minimum error. Let's try one final practice problem. Take the function f of x equals 3x cube plus 10. To find the derivative, we use the power rule. The 3 comes down to multiply the 3 in front, giving us 9, and the exponent decreases by 1. The constant 10 disappears because it has no rate of change. This gives us a derivative of 9x squared. If we want to find the slope when x equals to 1, we plug that in.
resulting in a slope of 9. By mastering these rate of change calculations, you now have the foundational tools to understand how AI systems optimize their behavior to